Let's have another look at related rates with another example, another two examples. Okay, we have a conical flask. Now, a conical flask is not a cone shaped. There is a cylindrical part at the top, but for the sake of this argument, for the sake of this example, let's call our conical flask a cone and have the cone represent, the mathematical cone represent our conical flask. So let's say we have a conical flask with a radius of 5 centimeters and a height of 12 centimeters, and it's being filled with powder at a constant rate of pi centimeters cubed per minute. Okay, and the first thing we want to find is find the rate in terms of height at which the height of the powder is changing. All right. Okay, so the powder forms a conical heap at the bottom of the flask, and we can represent that heap by this bit here. So we've got our nice red looking coloured powder, if you like. There we go. Okay, there's our powder, and it's conveniently forming a conical heap. Our conical flask is cone shaped, not quite the usual conical flask of chemistry. Okay, we know that the is filled with powder at a constant, our red powder is being filled at a constant rate of pi cubic centimeters per minute. That's cubic centimeters per minute, pi cubic centimeters per minute. The volume for a cone is V is 1 on 3 pi r squared times height. Here's the radius, here's the height. Okay, so that's the volume of a cone. All right, now our powder is being filled here. You can see in the red bit here, it's forming a conical heap as well. So it's forming its own little right-angled triangle down here. Okay, and we can look, we're interested in the rate at which the height of the powder is changing. So as it changes, it's going to fill up and keep filling up and forming this conical heap ultimately until the cone itself is full. Along the way, at any instant, it's forming its own little conical shape, its own cone shape within the larger cone. So we can use similar triangles here. This bit here we can call the radius, r, this bit here the height, and for our original conical flask of height of radius 5 centimeters, so our original one is radius 5 centimeters and height 12 centimeters, okay, we can form, by similar triangles, we can form the ratio h to r is equal to 12 to 5, okay, so r over h is the same as 5 over 12, and rearranging that, we can solve for r to give us r is 5 times h on 12. Okay, so important bit of information allows us to draw a little conical heap within the cone, within the original cone. Now, from our rates, we have dV dt is dV dH times dH dt, and I just have to remind you here that this is equal to pi units, pi cubic centimeters per minute. Okay, now V is 1 on 3 times pi times r squared times h. Okay, and where the r is, we can replace with 5h on 12, so that'll all be squared. When we tidy that up, we're going to have 1 on 3 pi times 25 on 144, 12 squared 144, 5 squared 25. H squared here times h gives us h cubed. Okay. All right, now within this related rate here, there's this dV dH term. Okay, this dV dH, and we know what dV dt is, that's pi. We would like to work out dV dH because ultimately it's this we want to know. How is the height changing with time? Okay, we know how the volume is changing with time. We'd like to know how the height is changing with time, and that's the height of the conical pile. All right, well, dV dH we can work out from this expression here. This is just a function of h only. All right, the only variable in there is h, the height. So dV dH is 3 times 1/3 times pi times 25 on 144 times h squared. Tidying all that up, we have 25 pi on 144 times h squared. So we've now got this bit, and we know what this bit is. So it's just this last bit we'd like to be able to find. Okay, now we know that dV dt is pi, okay, times dv dh, that bit in there, that's dv dh, times dh dt. Okay, well, that being the case, we could cancel the pi's here, as we've done, and we could solve for dh dt. So dh dt gives us 144 on, this becomes 1 here, pi goes here, this becomes 144 on 25h squared, okay, centimetres per minute. Remember our units were in centimetres and minutes. Okay, so dh dt becomes 144 on 25h squared centimetres per minute, and that's the rate at which the height of the pile of powder is growing. Let's have a look at another example now. Okay, we're interested now at the rate at which the radius of the powder is increasing when the height is 8 centimeters. So at the instant the height is 8 centimeters, okay? Well, we form another related rate. This time dv dt is dv dr times dr dt, okay? And we see that dv dt we know is pi from earlier, and the volume here, we want ddr of that, okay, so which is 1/3 pi r squared times 12r, because remember it was 1/3 pi r squared times the height. Remember the volume here was 1/3 at the top of the page, pi r squared times the height. Okay, I'll just show you at the top here just to remind you. Okay, 1/3 pi r squared times height. Okay, and the height, if we were to rearrange that, we would have from here, the height is 12r on 5. Okay, and that's what we have down here. Okay, so ddr, we want to find the derivative with respect to r of that expression, times dr dt, which we don't yet know. Okay, well, tidying this up, we've got pi r squared on 5, because we had an r cubed here. Okay, so differentiating that gives us 3r squared, but there's a third here, so that cancels out, and we're left with pi r squared 12 on 5 times dr dt. Okay, now dv dt we know is pi, dv dr we now have 12 on 5 pi r squared, okay, times dr dt. Well, we can cancel the pi's from both sides there, and that tells us that we have 1 is equal to 12 on 5 r squared dr dt. We then solve for dr dt. Okay, although, sorry, my apologies, first we can get rid of the r squared by putting in, you remember what we found earlier at the top here, we found that the height, we found, I'll put it over here, up here, all right, the height was 12r on 5, and my apologies, we want to put r in there, sorry, we had r as 5, whoops, r is 5h on 12, that's better. Okay, and so in here where the r squared is, we can place that, so we get 1 equals 12 on 5, 5h on 12 times, to power 2 squared, times dr dt. Okay, solving now for dr dt, we'll have 5 on 12 times, in brackets, in parentheses, 12 on 5h all squared. Okay, when we tidy all that up, we're going to have 12 on 5h squared. We're going to have h squared underneath, 25 underneath, a 5 up the top, so they'll cancel out, leaving a 5. A 12 squared here, we'll cancel a 12 here, so we're left with 12 on 5h squared. Okay, and then at the instant, when h equals 8 centimeters, we can work out what dr dt is. That's the rate of change of the radius of our pile of powder with respect to time in minutes. And so substituting h is 8 in there, we'll have 12 on 5 times 8 squared, which will give us 3 on 80 centimeters per minute. All right, I hope that one's all right.